Good morning, everyone. I'm Ahmad Aljohani. I'm studying PhD in the field of networking and cybersecurity at University of Canberra in Australia. I appreciate your time and attention and your patience for today. My presentation focuses on a hybrid shabby additive explanation recurrent neural network model for predicting and explaining distributed denial of service attacks on IoT networks. Let's start by setting the stage with an overview of what I will cover today. Introduction, literature review and research gaps, modeling, methodology, results, findings, and deduction. I will start by discussing the research problem and the motivation behind our study. The study focuses on resolving the problem of detecting attacks in IoT network, especially distributed denial of service, using explainable artificial intelligence techniques. We aim to determine possible attacks and interpret the decision made by our prediction system, as well as explain the architecture and structure of the used system to understand how the system reacts and how attacks happen. At the beginning, let's talk about the the denial of service. It involves overwhelming the server resources and network bandwidth to make it impossible for regular users to access it. A distributed denial of service attack is when a lot of computers or devices flood a website or network with fake requests, causing to slow down or crash. There are different types of distributed denial of service attack, each with its own tactic. Some simulate regular requests, while other target specific parts of the network, like wireless connection or data collecting sensors. The literature review discusses and summarizes recent research studies on explainable artificial intelligence application across various domains, including machine learning interpretability, smart monitoring, cybersecurity, and intelligent infrastructure defense. Authors in these studies highlight the importance of explainable artificial intelligence frameworks in enhancing interpretability, explaining machine learning algorithms, and promoting transparency in decision-making process. The table outlines methodologies, applications, and key findings from each study. Overall, the literature review showcases the potential benefits and challenges of explainable artificial intelligence techniques in improving machine learning workflow. In the modeling, we have 4 functions, F1 to F4. The first one, F1, aims to maximize the degree of privacy of the node. The second one, F2, aims to maximize the level of confidentiality of each node. The third one, F3, concerns the degree of security. And the last one, F4, is interested in the degree of trade-off between confidentiality and privacy. Methodology. The figures shows that the difference between artificial intelligence and explainable artificial intelligence lies in the transparency and interpretability of the processes. Explainable artificial intelligence aims to improve user experience by enhancing trust in artificial intelligence judgment, emphasizing the need to understand and regulate machine learning process for accurate artificial intelligence model. Outcomes. This is different from traditional artificial intelligence, where it's not clear how it works or easy to understand. Recurrent neural network is a type of artificial neural networks, and it's used it's used to detect distributed denial of service. RNN can handle data that comes in a sequence where each step relies on what happened before. This is important for detecting cyber attacks because hackers often carry out their attacks in a series of steps, which makes RNN efficient tool for detecting attack. Shabili additive explanation helps us to understand why a model made a particular prediction by breaking down the contribution of each input feature. It shows us which feature had the most influence on the prediction and how they affected the outcome. This makes SHAP values help us understand machine learning model better than other methods by giving us more accurate and dependable explanations for how the model makes prediction. Recurrent neural network, Shabili additive explanation. Model SHAP-RNN model detects and explains distributed denial of service attacks in IoT networks. The model aims to enhance the interpretability of the RNN network in identifying these cyber attacks. It includes training the RNN on network traffic, computing SHAP values for each input feature and output, visualizing the SHAP values to understand feature contribution, and improve the model based on these insights. The methodology focuses on explaining the decision made by the RNN network and enhancing its performance in detecting and identifying distributed denial of service attack. And there is specific consideration given to the internal hidden state of RNN model. The provided figure illustrates the artifact design process for enhancing recurrent neural network with explainable artificial intelligence for detecting distributed denial of service attacks. The design involves data collection from various sources, data pre-processing to prepare it for RNN input, feature engineering to extract relevant element, model selection, integration of explainable artificial intelligence techniques like attention mechanism, algorithm design, training, implementation, and finally evaluation of the model's performance. The goal of RNN-SHAP for DDoS is to efficiently identify distributed denial of service attacks while ensuring clear decision-making process. Only a small number of studies have looked at improving and explaining recurrent neural network with shabby additive explanations. Others have concentrated on using recurrent neural network to deal with distributed denial of service attacks. Our contribution is to use shabby additive explanation to explain how recurrent neural network works in solving the distributed denial of service problem. By using RNN-SHAP for DDoS, we can understand better what affect the model predictions and make it better at detecting distributed denial of service cyber attack. The used dataset is UNSW MB15, and it's a dataset used for cybersecurity research and specifically for network intrusion detection system. It contains network traffic data collected from a real-world environment. The dataset includes various types of network traffic, both normal and malicious, making it valuable for training and evaluating intrusion detection system. Researchers use UNSW MB15 to develop and test algorithms for detecting and classifying different types of cyber attacks, such as denial of service and distributed denial of service attacks. The table provides a breakdown of the data set by attack type and the number of records available in the dataset for training and testing purposes. The result, the given figure shows the evaluation of the accuracy metric for RNN-SHAP. The formula calculates the accuracy rate based on the number of true positive, true negative, false positive, and false negatives in the model's prediction. Here in the result, we have three tables. The down table shows the confusion matrix of testing instances using RNN-SHAP, detailing the correct predictions for anomalized and normal instances. The top left table present the values of metric during the training phase for different algorithms. The top right table displays the metric during the testing phase, comparing the performance of algorithms like RNN, RNN-SHAP, GRU, RNN, SVM, and random forest. These tables provide a comprehensive comparison of the algorithm's performance in both training and testing phases. And we can clearly see that RNN-SHAP has the best performance. ROC, receiver operating characteristic analysis, uses the ROC curve to assess algorithm behavior. The figure illustrates the ROC curves for different algorithms, showing the trade-off between error and true positive values. For example, the ROC of RNN-SHAP achieves 95% true positive values with 10% error prediction. Temporal complexity analysis evaluates the training time of algorithms. Even though RNN-SHAP works well, this figure shows that it doesn't train faster than other methods. This analysis highlights the importance of considering training time as metric for assessing algorithm performance. Finding and deduction. The research aims to bridge the gap between machine learning and IoT security by creating machine learning models suited for detecting online threats in IoT networks. It uses explainable artificial intelligence to address the challenge of detecting threats in IoT environment. Explainable artificial intelligence allows for artificial intelligence solutions to provide explanation for how intelligent devices operate within their context. While explainable artificial intelligence shows promise in the detecting IoT attacks, there are still many unexplored possibilities that may emerge in the future. However, it's important to note that the UNSW MB15 dataset used for evaluation in this study may have class imbalance issues where some attack types are less common than others, but potentially affecting the training and evaluation of machine learning models. Thank you so much for your listening.